so Weaver State Canvas, and then we'll go to the 11:15. I'm all cut up on grading labs and the signature assignment. So if you turn something in, I should be able to have it graded quite quickly. So keep that in mind. You can look at your feedback once I have it graded. Modules. Lab 12, PreLab. Okay, so this is a little bit different than it is in the PreLab. So let me kind of stop. You guys keep the instructions. I think that one like when we did the I think we would go like sort of like like this is like no, I'm just not gonna do that. That's literally like you give sheriff so you can be the auditor or something. You can have auditor. Yeah, we have to be so this one, you'll have to write a report.
We just recessed, so someone. Oh, that's my shirt.
Yes. I thought you could be the farm. You can only find it later. Gravel pit or the first gas station. You can actually, Kayla, you've been protesting by the It'll basically turn into like a gravel pit. Okay, perfect. Thank you. Okay, so this lab. This lab is a little bit different. The only thing that we're doing in the lab is you're going to take pH paper and you're going to measure. There's 26, what's the biggest number? 27. There's 27 samples, so I already have those out. They told me what pHs to put in them. And so what we're doing is the 27 samples came from the different places on the map. Okay, just theoretically. And so there's a topographical map. Does anyone know how to read this? What do you mean by this? Okay, this is the top.
And then the river goes this way.
The river goes this way. Okay.
So this is downhill.
Okay, this is downhill.
This is the big.
Okay.
It's just the elevation change on the map.
Yeah, and you can see these are good. These lines are the elevation changes. So you can see one's at 95. I don't know what units they're using. Probably not miles. Kilometers. Oh, it says that. Oh, thank you. I'm not sure. Do you think this is also kilometers? 95, 90, 85, 80? Maybe.
Or meters.
Or meters. I'm not sure.
I don't actually know.
Yeah, I'm not sure what unit, but it could be kilometers. I think that's the best guess because it has kilometers. Okay, so what happens if the lines are close together? What does that mean?
That is like a steeper.
Yeah, so lines that are closer means it's steeper. That's one of the post-lab questions. So then it kind of gets flatter next to the river. That makes sense. And then it's kind of flat. Okay, so you have to kind of think like, what's going to happen to water that is on a steep slope? It's going to go down. Okay, so you have to think about, you're going to look at some pHs, and you're going to try to see, okay, you're going to label the pHs on this map. So, for example, what happens, I don't know, what happens if next to the gravel pit, you have like this pH of 0, and then around it, these ones that are getting closer to the river, are still like pretty high, like maybe 2 or 3, or like even 5 is a pretty high pH for the environment. We could say, oh look, it looks like it's coming from the gravel pit because that was a high pH and the water looks like it's going to travel down. So so let's start back to the beginning. So you're going to be testing pH, and you have to imagine as if this city, they're having some water problems. You are looking at their water samples and you're going to tell them what the problem is based on your evidence. Okay? So your evidence would be the topographical map and the pH. Okay? Let's see. So what you have to do is, I'm trying to find it in here. So you have the groundwater samples. This is what you have to do. So imagine that this city has hired your company. You can work in groups of 2 or 3. The PreLab says something about groups of 4. That is at Weber State. They can have groups of 4. So you can work in groups of 2 or groups of 3. That's what Weber State told me. I asked them specifically because it was getting confusing. So 2 or 3. All right. And also this doesn't match. It says partners, groups of 2 or 3. So you need to include this in your write-up. So imagine you're a company. So like maybe if you go to school, you get out, this could be a job. Okay, so kind of real world scenario. You're going to put the pH measurements onto this table. This is part of the report that you're submitting. Okay. So label the pHs, and then you also have to color code the pH. One idea would be, a lot of the time we use red for acidic and blue for basic, and you could use like a white for neutral or like gray for neutral, okay? Or you could pick your own color. Maybe I want green to be acidic, and maybe I want purple to be basic, and I'm gonna label it based on that. So that means you probably need to provide a key so that the city, when they're reading your map, when you're color coding, like look at the green spot, can you see it's acidic? They know what they're looking at, okay? Let's see, so you're gonna, pH measurements, you're going to determine the direction of groundwater flow using your well monitoring data and the topographical map. So that's what you're gonna use this, okay? So be based on, it's really steep here, the water's gonna go down. The river is going this way, the water is gonna go that way also. Okay. So, identify the problem area or areas. Once the problem area has been identified, draw several arrows showing how water flows through the contaminated area to the river. So if we decide that the gravel pit is doing the contamination, we can show, oh, it's going down the hill to the river, and that's why these ones are a higher pH or lower pH. Maybe it's basic. Okay. Questions so far? Are we kind of getting the idea? Okay. When you write a report, so this is a 5-paragraph essay, and it's really nice. It walks you through exactly what you need to write in each paragraph. Okay. When you write your report, imagine that the people who are reading the report, they do not know what you are talking about. You have to guide them. You have to say, look in this figure, and tell them exactly everything that you know. Okay? And so I think that'll make the paper easier than you think. You need to put more details than you think. Okay? Tell them what figure to look at. Tell them where in the figure. Tell them what color they're looking for. Tell them what arrow they're looking for. Be really specific. Guide them as they're reading the report. And that will help it be really clear. And that will also, I think, help it go. You will just be able to write very detailed, walk them through what they're looking at. Even if you think it's obvious, write it in the paper. Okay. And that's what I found when I write papers is just make it really, really, really obvious. Write everything out. So paragraph 1 is it just walks you through. Who is responsible for the groundwater contamination? Based on your claim. And then it says, also state how you're going to prove it, what data you're looking at, groundwater flow. Okay. And then your 3 paragraphs. Paragraph 2 is include the data table. So show the data table. You can just like take a picture of this and stick it in and use that as your picture and say, look at figure 1. Notice in figure 1. Look at all the pHs in figure 1. This is what we noticed about the pH. Be very descriptive. You can write everything that you see in this figure in the paragraph. Okay. So basically, paragraph is you're explaining exactly what you have gotten from the data, the pH data. Paragraph 3 is groundwater flow analysis and color pH. So that's using the site. So that's also this one. Groundwater flow means you're looking at these dots and you're going to highlight them based on the pH and you're explaining what you see there. Okay. So the first one is pH. I know this is the range of pHs we see. There's this one that's concerning. This is also concerning. And then the groundwater flow is like, oh, it looks like these ones are related. It looks like it's the river is getting more acidic or more basic. Okay. And then paragraph 4 is a topographical map with a legend. You should color code this one. Does it say that? So do what it says. But it might be helpful to, I think this one's the one you have to have arrows showing it's steep here, we're drawing arrows to show where the water is flowing. Okay. And so walk them through that. Look at this arrow, see how it's steep. Look, it says 95, then it says 90, then it says 85. That means it's steep. I have an arrow there, the water is flowing that way. Okay. Then conclusion paragraph is bringing back everything together. So make it obvious, repeat things, tell them where to look. Make it very clear why you are saying that. For example, maybe the gravel pit is contaminating their water. They need to have clear evidence. So if they need to go after this company, like legally say, like you cannot work here anymore, they need clear evidence of that. Okay. In your paper, you also have to include your company's name somewhere, and then you're going to submit it on Canvas. And the paper says everyone needs to submit it. So everyone needs to submit it. Okay. So if I'm working on a Google Doc with my partner, I need to submit it, even though my partner submitted it. Everyone needs to submit it. Okay. All right. Let's see. So I think the biggest part of this will be writing the essay. We're measuring the pH, but that's not going to take very long. Okay. On Friday when you come, we'll have the lab open. There will be sample vials, and they have numbers on them with Sharpie, so it shouldn't come off. And I'm just going to put them around the lab, so like 4 at each station or something, with pH paper, and then you kind of rotate through, and so hopefully it's not going to take very long. So I think I just need 1 set of samples. I think that'll be okay. Rotate through, get the pH data, and then start your paper with your group. Okay, questions on that? Okay, great. Let's look through the pre-lab. The first one is with your group, come up with the name of your company. So do that. Question 2 is kind of helping you think about who's going to do what. So think about who's doing what. This one, question 3, just put NA. Question 2 will mark you wrong because it's for some reason that it's not like a teacher graded question, so I just go back and give you the points. So just be aware it will mark you wrong, but that's just because we restate however they put it in is kind of weird. Yes, question 3 just put NA. How will data gathering assignments be carried out? Who's in charge of each water sample? So that's like, I'm going to measure half, you're going to measure half. Or like, you just do the pH. I think everyone should probably measure pH, but you're going to measure 1 through 10, I'm going to measure 1 through 27. Or 10, 11 through 27, something like that. And then what are you going to color code? Are you going to use red for acid, blue for base? Are you going to use like a different color scheme? Are you going to use like shading, like are you gonna do like no color means acidic, and then like as I shade more, maybe that would mean that it's more basic. Okay, so how are you gonna color code the map? Explain how the topographic map lines work. So we talked about that. The closer lines are steep, and then the lines on the edge of the lines, it tells you the height or the elevation. Probably elevation is a better word there. How can you determine which direction is downhill on the topographical map? Well, the numbers get smaller. So smaller numbers is lower elevation. So it's going to go downhill. So this is going downhill. This is going down. Or okay. All right, so I'll give you a minute to do that. While you're doing that, I'm going to pull up Alex chapter 13, and I'm also going to pull up our chapter 13 notes for day 2. Questions about the pre-lab for lab 12 before we start? Okay. Yeah, talk to you about oh yeah, if your partner's not here, or
Sure. Who do you usually go with? Ashley can just join our group, because we can have 3, right? Yeah, that'll work. Okay. Gosh, she just. So, what's our name be?
yeah, names have to be appropriate. I'm not sure.
Okay,
Perfect.
I should have matched our names together.
Oh, okay. Okay, I don't have like I'm not sure. Just to be clear.
Test code.
Names have to be
Test code.
or I have to go
I'm gonna do test code. Test code? Like that? Okay. In charge of what? Do you want to do the letter writer? Sure.
So like one person doesn't write the whole one.
Yeah. Just,
Oh, but like
yeah.
you could be in charge of that sign.
Okay, so Corbin, CR. And then I know the mine is graph analysis, smashing is that one. What's your Ian, right? Just put ash for the pH well shape. Yeah. And then question 4. Yeah. You just split the. We will split the testing.
Oh.
Is that, do we do more do we do more to question 4, or do we just say we'll split the pH testing between us? And 5, I just put red for acid, blue for base, and gray for neutral. Red for acid, blue for base, yeah. And then we should say like the darker it is, the more of it is like, you know.
I'll give a letter writer.
This is what we draw last. Did anyone else who needs the chapter 13 notes sheet?
I know,
That's everything, right?
Oh, what kind of is it? I think we should. Okay.
Oh, yeah.
We just did.
I'm not yet.
Okay. So you guys can do all in the same group? Yeah, will that work?
Yeah, it's adding my.
I think she's dropped. She does that. And then the way you're working with her is she's going to be so what is
Love that.
So on question 3,
Does we kind of have a yeah, we were saying so we're in two. Yeah, I guess you're on six.
Because I.
Okay, let's do 2 more minutes to wrap up your pre-lab, and then we will start we'll finish up chapter 13. Oh yeah, so like every single
I was kind of like the higher the pH, and I felt
it'll be like it's just all
okay, let's do acid. Now I have a day.
I just finished writing last week.
I have a day, but now I'm like accepting. For me, it's Amelia as a girlfriend. Yes. She says to me as
Okay, here we go. We're gonna finish with central isomers and hydrogenation and hydration. Okay, so isomers. We talked a little bit about isomers last time. This time we're going to talk about. Oh, I have drawn on here. Constitutional isomers. That's if they're bonded differently. That's what we talked about last time. Like the bromine is connected in the middle, or the bromine is connected at the end. Stereoisomers are isomers that only differ in the 3D arrangement. So when we are looking at these, we are looking for a double bond, and then the arm of the double bond is either pointing one way or it's pointing the other way. Okay, so all the atoms are connected the same way. They have the same chemical formula, but they're just like bent differently across the double bond. So let's see. Let me get rid of my drawing. Sometimes I leave my drawings in there for people to look at, but we'll get rid of that. Okay, let me see if there's other drawings I need to delete. Okay, we're good for a minute. Okay, so look at these examples. These two are constitutional isomers. So they are, can you see how the double bond is at one end? And then the double bond is in the middle? So that's a constitutional isomer. Okay? They're connected differently. This carbon has a double bond versus the second carbon has a double bond. Okay? And then a stereoisomer is can you see how on this side the methyl groups are on the same side, and this one the methyl groups are on opposite sides? So the only difference between these is the arrangement of the methyl groups around the double bond. Okay, they all have the same formula. They are all connected to the same atoms, but this one, the double bond, is in a different spot. From here to here, the methyl groups are rotated differently. Okay, and this is because, remember we talked about the double bond locks the molecule. Okay, so this molecule will behave differently. It will have different chemical properties than this molecule, and that's why we care, because we need to identify if it's a stereoisomer, because they have different chemical properties. Okay, they're different molecules, even though they have the same chemical formula and they're connected almost identically. The only difference is one's pointing up and one's pointing down. That's a stereoisomer. Okay, so when the methyl groups are on the same side, that's called a cis isomer. If the groups are on opposite sides, that's called a trans isomer, on opposite sides. Okay, and so then we tell you what side. So we're going to be looking at like little branches, but whatever side the two biggest groups are on, if they're on the same side, that's going to be cis. Oops. And then we put the location of the double bond. Oops, I'm going the wrong way. And then if it's on the opposite side, if the two biggest groups are on opposite sides of the double bond, then that's going to be trans. And then we tell where the double bond is, 2, and then our parent chain, butene. Okay, so some more rules to follow. So this is oleic acid. This is a cis isomer. Have you heard of trans fats? Okay, this is the next picture. So this is oleic acid. This is the trans version of this molecule. And the only difference is that the two groups are on opposite sides of the molecule. This is energetically harder this is like more stable. So it's harder for our bodies to break down, and that's why trans fats are bad. Okay, so cis, that's easier, that's more energy unfavorable. So it's easier for our bodies to break down, and that's why those are better for us. Okay. And saturated fats are ones that have no double bonds, completely use up all hydrogens. It's saturated with hydrogen, saturated with hydrocarbon. Okay, we're going to do examples in Alex. Okay, the next two things we need to talk about are reactions. So once you have double bonds, they are a little bit reactive, and so we can predict chemical reactions. And this is a lot of what organic chemistry is. If you take the year-long class at a university, you predict all sorts of reactions based on either reactants that you have, or you say, I want to make this. How could I make this? And based on what you know, you can predict how you can make that chemical, okay? And so this is just a little bit of that. So alkenes undergo, this is called an addition reaction because we're adding something, where we get these two, so we have this simple molecule made of X and Y. This is our model molecule. X and Y are added, it's called added across the double bond. So wherever the double bond is, X and Y replace the double bond. Okay? And so I kind of imagine one of the bonds is like unfolding. We have 2 electrons, remember 2 electrons make a bond, and then 2 atoms can bond to those new spots. Okay? So if I have a double bond, I can do an addition reaction, and we get 2 single bonds formed onto this double bond. You see that pattern? That's the pattern we're going to be looking for and predicting, okay? Okay. And I think this is on your notes sheet. Yeah. Okay, so here are some other alkene reactions. So these are all addition reactions. So you could add hydrogen. When we add hydrogen, we always use a metal catalyst. And one of the Alex topics asks us about that. some of the catalysts we can use are nickel or palladium, Pd, or platinum. Those are very common hydrogenation catalysts. Those are really good at promoting this reaction. So we have our double bond in our molecule. We need hydrogen. We add a catalyst to speed this up, and the hydrogens add across the double bond. That's called hydrogenation. We can do things like halogenation. So if we need chlorines here, we can add hydrohalogenation. So that's if we have hydrogen and a halogen. So like if we add HCl, we'll get one chlorine on here. Or we could add water. If we add water, this is, we need an acid catalyst. This is called an acid catalyzed reaction. That just makes this reaction go faster. And we're not going to talk about the mechanism. Mechanism is like how it does it. Organic chemistry, you will also talk about like what's going on. Why is this happening? And you can draw where the atoms are going. We're not going to do that. This is called a hydration reaction. So we're going to focus on hydrogenation and hydration in our class. But there's all sorts of other reactions. If you are interested in that, that would be organic chemistry. That's what you would talk about. Okay, so hydrogenation is when we take the double bond, and instead of the double bond, we just have two hydrogens on the double bond. Okay, so basically, in a skeletal structure, it looks like the double bond disappears because we had two groups, and now we just have hydrogens there. Okay, so we start with an alkene, and we end up back to an alkane saturated. So that's your tedious. So we need a catalyst for hydrogenation. We talked about that. We're going to use usually palladium, but we can also we can use nickel catalysts and platinum catalysts, and we'll talk about how to put that in Alex. If you have multiple double bonds, if I have two double bonds, then I'm going to need, for every molecule, I'm going to need two hydrogen molecules because I need one hydrogen molecule per double bond. So that's going to be an Alex. All right. Hydration is like the same thing. The same thing is happening. We have our water. One of the pieces of water becomes hydroxide, and one becomes hydrogen. And we do this in the presence of an acid catalyst. This is an acid catalyzed reaction. So we need some acid like H2SO4 or H3PO4. Let's see. And then we have an extra rule. If the carbon atoms that the groups are adding to, so we're going to add a hydrogen and a hydroxide. Doesn't matter if it's identical, okay? But if there's substitution on the double bond, so like this one has a methyl group, this one just has hydrogens, oops. Then we have this rule. We have this chemist came up with, he observed this, and often it follows this. It's called Markovnikov's rule. The OH, so remember we're adding, in hydration, we're adding an H and an OH. The OH goes to the more substituted carbon. So if we have this double bond, the OH piece is going to go on the group that has more carbons, the more substituted carbon. And the H is going to go on the other side of the double bond. So it does matter what side it's going on if it's unsymmetrical. All right, I think that's all. And I think that is in there also. Let's go to Alex and do our last four topics. So let's go. The first one says, draw the cis or trans isomer. So this one's draw the skeletal structure of cis. That means the two groups are on the same side of the double bond. 2,5-dimethyl-3-hexene. So I'm going to draw the parent structure first. This is skeletal. Make sure you draw the right type of molecule. So 1, 2, 3, 4, 5, 6. And they're pointing opposite ways. 1, 2, 3, 4, 5, 6. This is, let's see, let's find the double bond. The double bond is at the 3 position. 1, 2, 3. So from 3 here, oops. So there's my double bond. Right now, this would be the trans isomer because this group and this group are on opposite sides of the double bond. So like if I draw a line through my double bond, one group is above and one group is below. Can you see that? So what I can do is I can take my this hand tool and I can move this. So now I'm gonna try to make it kind of like that. So we've got 1, 2, 3, 4, 5, 6 still. Okay, but can you see how those groups are on the same side of the double bond? That's a cis isomer. Okay. 2, 5 dimethyl. So at the 2 position, oops, I am on my finger tool. There we go. 2, 1, 2, 3, 4, 5 dimethyl 3-hexane. Let's check. This one might be picky. Oh, great, it's not picky. Okay, does that make sense? Okay, let's do another one. Naming or drawing. Okay, next one says draw the skeletal structure of cis 4, 5 dimethyl 2-hexane. Did we just do this one? No. Okay, so hexene 1, 2, 3, 4, 5, 6. 1, 2. There's my ene. And then can you see what this right now is? A trans isomer. They're on opposite sides of the double bond. This one's below it. This one's above it, I guess, if I cut it like this. Can you see that? Okay, so this is kind of tricky for students in the class to see. All right, so I'm just going to move this one. Now it's cis. Now they're on the same side. Remember, around the double bond, those groups are locked. That's why this is important. Okay. Any of these other single bonds, the molecule can rotate. It can spin around freely. But because this double bond is here, that's why we have to specify if the groups are on the same side or the opposite side, because it's locked in that position. That one cannot rotate. Okay. All right, so we've got our cis dimethyl, but we need the dimethyl. So we've got 4. So this is 2, 3, 4. Oops, I'm on the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Dimethyl 2-hexene. Let's do another one. This one says trans 2-hexene. So 1, 2, 3, 4, 5, 6. And then it doesn't matter which direction 2 is. Oh, 1, 2. So there's my double bond at the 2 position. And this one's already trans. Okay, so I can just leave that. No substitutions. Let's do one more. This one says pentene 1, 2, 3, 4, 5. Pointing in the same direction because it's odd. 2 pentene, so I'm going to put it at the 2 position. Oops, what's going on? 2, there we go. And then trans. Okay, so I'm going to check my double bond. If they're on opposite sides, this one's on one side, this one's on the other side, that is trans. So it's already trans. 4 methyl. 1, 2, 3, 4. Okay, do you guys feel okay about that? That's something that I practice. In the past, that's been confusing to students. So I would put some time into that one.
Wait, so cis means they're on
the same side. Cis is same.
And what are we comparing it to the same side? Like same side of what?
Same side of the double bond. So if I draw my double bond like this, that's cis. That's trans.
Oh, okay.
I always think this is like train tracks. We're on the opposite side of the train tracks. Okay. All right, let's do the next topic. Oops, I did it. Okay, next one is identifying cis-trans isomerism in a condensed small structure. So this one's also kind of tedious. So check the box under the compound that exists as a pair of cis-trans isomers. If none of them do, check the box none. So when we go through this one, what we're looking for is we have to have different groups on the ends. Okay. So for each one, we can decide, is this, could we have this in a different version and it would be a different molecule? Okay, so let's draw this one. So can you see how we have 2 different groups at both ends? For the top left box, that's what this one is showing. This could also live as this. Do you see how these are on opposite sides of the double bond? These are on the same side. So this one could live as a cis trans isomer. So this would be like our cis, this would be our trans isomer. Does that make sense? So this one we could say, yes, that one is cis and trans. This one, let's look at this one. This one kind of looks like this. Yeah, this one we have a hydrogen. So this one we have the methyl groups could point the same direction, or the methyl groups could point different directions. So that one could also be a cis-trans isomer pair. This one cannot, because it has two of the same group on both ends. It has to have different groups on both ends. Okay. So this one is like, could be, what do they have? Two methyls. Could be like this, or it could be like this. Okay, that's the same. Even if I like flip the methyl groups around, that's the same. Okay, so that one doesn't. And then the last one, we could think about it like this. So we have this one. Oh, those are hydrogens. No, they're methyl groups. Okay, so we have this, or we could draw it like this. We could flip these. But because I have two of the same group on this end, this is just a mirror image. This is the same molecule, just rotated. Okay? Can you see how this is a different molecule? The cis and trans version. This is the same molecule. I can just rotate this and it's the same. Does that make sense? I cannot rotate this and get it to fit in this molecule. Okay. All right, so the two bottom ones cannot be isomers. All right, so then we look through. So these have two different groups at both ends. So that one is going to be able to, we could have both methyl groups pointing up, or one methyl and one pointing up and one pointing down. That would be, we could do that. This one has an OH at one end and another OH. So that's going to be like this one, where it can't, it can't be, like, even if we flip it, it's going to be the same. Because it has two of the same groups on one end. So that doesn't work. This one, we could have both of the chlorines pointing up, or one chlorine pointing up and one chlorine pointing down. So this one would be, could be isomers. This one has two methyls. This one we just did this one. Even if we flip the two groups, because the other end is identical or symmetrical, then it can be an isomer. Okay, for time, we're gonna head to the next two topics. We've got 8 minutes of class left. So the last two, the first one is predicting the reactants or products of an alkene hydrogenation. So can you see how this is an example? This has two double bonds. So we need two hydrogen molecules to saturate these two double bonds. For every double bond, we need one hydrogen molecule. And they're saying it's in the presence of platinum, the catalyst. This is a condensed structure. They're saying draw the structure that we expect here. So this is going to be, it's going from a double bond molecule to something with no double bonds. So I'm just going to draw, the end will be CH3, and then we're going to draw CH2, and then CH2, and then CH3. So we're going from something that's unsaturated to something that's saturated. Does that make sense? All we're doing is saying, okay, instead of this double bond, I'm going to put a hydrogen here and a hydrogen here. Okay, so now this has, instead of one, it has two. Instead of two, the end one has three. Instead of one, it has two. Instead of two hydrogens, now it has three. We're just adding a hydrogen to both any carbon that's connected to a double bond.
It's already CH3. Can you do CH4?
No. No, that means, so like, only if it's connected to a double bond. Okay. That sounds like it's not connected to a double bond. Okay. Okay, so we have to predict the product, and sometimes we have to predict the reactant. Okay, this one's not. Oh, yes. Give one possibility for the mystery reactant. So if this is, we have to identify, H2, that's a hydrogenation. That means we'll get an alkane. We're adding across a metal catalyst. So this R group, or this is our unknown. This is going to have a double bond somewhere. Doesn't matter. This one doesn't matter where. I'm going to put it up here. Okay, if you get the same question, you put the double bond on the other side, it's the same molecule. Okay, does that make sense? You're just predicting what would this be? All right. For the following organic reaction, identify the mystery reactant. Its stoichiometric coefficient, N, and any other substance that must be present. So if I look at this molecule, I can see I'm seeing that this is a hydrogenation. We're getting rid of the double bond. So R must be H2. Oops. Is my caps lock on? Yeah. H2. How many H2s do I need for this molecule? Yeah, I need 2 because I need as many as there are double bonds. So this is a 1, I need 2 of these. So N is 2. Does that make sense? Just need 2 of those. And then is there any other substance that needs to be present? Yes, we need a catalyst. You get to pick. This is kind of exciting. You can pick whatever catalyst you want. I like palladium, so I'm going to put palladium. You can also put nickel or platinum, and it will accept it. Okay. So pick your favorite hydrogenation catalyst. All right, let's see what other types of this reaction. Okay, so this one, we're drawing the skeletal structure. Make sure you draw the correct type. If it's skeletal structure, draw the stick version. If it's condensed, draw the one with hydrogens and carbons. This one is, I think this type is easy. We're just drawing the molecule without double bonds. Okay. Hydrogenation gets rid of the double bond. Okay. All right, let's do the last topic before we run out of time, and then before we have run out of time. The last one is predicting the reactants or products of an alkene hydration. So we have a double bond, and we have to decide where does the OH go, and where does the H go, because water's going to split and add across the double bond. So I'm just going to draw the structure that's given, and then I have to add the hydrogen and the oxygen where the double bond is. Okay, the only places it can go is around the double bond. I think sometimes people are like, well, this one doesn't matter because it's symmetrical. But sometimes if there's a bigger molecule, people just put the hydrogen and hydroxide wherever they feel like. It has to go around the double bond. That's what makes this molecule reactive. Okay, so remember we have Markovnikov's rule. That means it goes to the more substituted. OH goes to the more substituted. So the more substituted means the one with more carbons attached to it. So if I look at this double bond, this one has a carbon group attached to it. This carbon is where the OH is going to go. That's the only spot it can go. So I'm going to put the OH right here. And then the H goes at the end. I don't have to draw the H because it's a skeletal structure. Okay, so don't draw the H if it's skeletal structure. We just know it's there. Okay, all right. So let's check. Okay, let's do another one. We got 3 minutes. So this one's asking for the product. H plus means it's an acid catalyzed. Okay. R is, okay, so this one, we have to decide, oh no, where is the double bond? Okay, so it looks like there is 1, 2, 3, 4, and then down. This one has a lot of correct answers, but can you see how there's a methyl group and a methyl group? So I'm getting rid of the OH, and I'm kind of imagining what it would look like. And then I have to decide where I can put the double bond. Okay, so this one has a few options. I could put the double bond here, because if I put the double bond here, that will show that the OH can go here, and that will be the more substituted carbon. Okay. The other option here would be drawing my double bond here, and this would still be the more substituted carbon where the OH would end up. So either of those should work. Okay. So we're just predicting. Does that make sense? How are we doing on this type of topic? Does that make any sense? Okay, do you think you could work through that? Okay, let's do one more. Predict the major product. Oh, And this one's condensed structure, so we gotta draw the condensed structure. So this one, I'm gonna predict that my my OH goes here because this is more substituted carbon on the double bond. It has to go on the double bond. So it can only go here or here. This one has more carbons attached to it, so it's gonna go here. So if I draw this out very painfully, then this is the carbon instead of, we're gonna have this OH. And this one I'm gonna have to go back and change and make sure that I have the correct number. So this one should just be a carbon now. Correct number of bonds to each carbon. Oops, this should be CH2. Okay. All right, if you have questions on this, let me know. We will do lab 12, last lab on Friday.